So let's say I want to write the electron configuration for zinc atom, the zirconium, Zr, zirconium. So the zirconium element, we first find out how many electrons. Zirconium has it's 40 electrons. Okay, so zirconium 40 electrons. It has 40 electrons. So the electron configuration start from 1s. So 1s2, 2s2, 2p6, 3s. And after 3p6, it should be 4s. And then 3d, 10. There are 40 electrons. So here we got a 10. Here is another 20. So together 20 so far. Plus 10 more. So far we have 30 electrons. After 3d10, it is 4p6. And so after 4p6, there are 4 more electrons. After 4p6, next should be 5s. To find out what the order for the electron configuration, use that off-ball principle. So the diagonal diagram. Some of you remember that. This is the 1s, 2s, 2p, 3s, 3p, 3d. Use that diagram to find out the order for the configuration. After 5s2, the next will be 4d. And so far I used up 20 from here to here is 20. I added 10 more. So here together 38. So I have 38 electrons to fit in the 5s2. And that means I have 2 more electrons. 2 more electrons go to the 42. So that's the electron configuration for the atom, transition metal. Next one, vanadium 3+. What is the electron configuration for vanadium 3+? Vanadium atom has 23. The atom, 23 electrons. And so vanadium 3+, it should be 20 electrons. To write a configuration for vanadium, you do the same. This time, I feel like we need to use a shortcut. Use the noble gas shortcut. Use the argon, because argon is one immediately before the vanadium. Argon is 18 electrons, so 2 more electrons. 2 more electrons. After argon, the orbital, the low energy subshell should be the 4s. But for transition metal, when they lose electrons, they lose the s electron first. So the configuration for the vanadium 3+ charge ion, it is actually there'll be no more 4s electrons. It's only 3d. Only 3d electrons. Because the transition metal, they will lose the s subshell electron first. So that's the configuration for the vanadium 3+. It's important to know that to write a configuration, lose s electron first. And last example, the molybdenum 3+. Molybdenum 3+. Okay, sorry. Okay. Okay, sorry about that. The molybdenum 3 plus, the same idea. You just lose the s electron first. Final configuration, which is have a 3d4, 4d3. So the molybdenum, you lose 5 s electron first. You end up have only the 3 electrons in the 4d subshell. So that's the electron configuration for the transition metals. We need to know how to write the ion configurations. Later in the chapter, deal with the transition metal complex. The number of electrons in the d orbital, it affects the magnetic properties. And that's, we start from here. Okay, so that's the configuration. I'll go very quick. Coordination complex. The transition metal tend to form with the ions or anions or molecules with long pairs. And that kind of bonding, it is Lewis acid-base bond. The cations, positive charge, form bond with long pairs from those molecules or ions. Those molecules, ions surrounding the metal cation, they are called ligands. They're called ligands. Is the one that is binding with central metal. The typical ligands are the water, ammonia, halide ions, some nitrogen compounds, because nitrogen has a lone pair on the atom. And coordination number is the number of ligands binding with the central atom. It can be 6 or 4 or 2. So those are the most common. In our class, we focus on the coordination number 6 most often. So here, this is the chromium form compound with ammonia as ligands. The chromium has a 3 plus charge. Ammonia is neutral. So we have 6 ammonia molecule binding with 1 chromium, form a complex ion with 3 plus charge. So these are the coordination number that is not 6. There are 4 of them. This particular copper ion has a green color. Copper can also form complex with water, and that's the blue color. Here, cyanide as a ligand form bond with silver ions. And when you have 6 coordination numbers, the geometry of the complex ion, it is octahedral. Okay, octahedral. When you have 4 ligands, coordination number 4, it can be either square planar or tetrahedral. Okay, we'll see tetrahedral later. These are the different coordinations and the geometry of the complex ions. Octahedral is most we focus more on. Each has its own examples. The ligands are the Lewis base. Metal ions are the Lewis acid. And with the metal form ligands, ligand can form bond. If one ligand form 2 bonds, that's it's kind of like teeth bind on the central metals. This we call a bidentate. Bidentate is when you have a molecule or ion have 2 locations can form. Okay, let's say this is a molecule have 2 locations. Each one have lone pair. Then they can form with metal 2 locations form bonding. So about the teeth holding on this. So bidentate. Monodentate means a single T's, and bidentate means two T's, bino is one. It can be even more than two, so it's polydentate. And so these are how each ligand they bind with the central. Bidentate are when you have two nitrogen in the molecule, and they can both form bond with the metal. Polydentate can be more than two. Chylate are the compound, one molecule has multiple places, and since multiple places same time form bonding, in the end they form a ring. And this we call a chelate. Form a ring, chelate. The chelate can be used for treatment for heavy metal poisoning, because the EDTA molecule, which have 6 locations to form bond, and that would be perfect for the octahedral. Is one molecule form bond with multiple locations, very strong bonding, and can use that to remove the heavy metal poisoning from our body. Coordination numbers has its own naming system, but we won't be spending time on explaining about naming, and it's pretty straightforward. This part is important. We need to know what is charged on the transition metal itself, given the formula of the whole compound. So this is an example. Let's say we have this is a complex compound. The potassium ion is a free cation. The anion is complex anion. You have a copper and multiple chlorine. So together have negative charge. That's complex cation. The complex ion, we use a bracket. So in this case, we look at the what is charged on cobalt. To think about the charge on cobalt, we start with the potassium. The potassium should always be +1 charge. And so that means with the potassium charge as a 2 positive, we can decide the whole complex ion is 2 minus. And that's the whole charge of the cobalt complex ion. And in this complex ion, there are 2 different kinds of ligands. There's ammonia as a ligand, and there's also the chloride as ligand. Ammonia ligand is neutral, okay, 0 charge. Chloride ion is -1 charge. So the whole thing, you have a cobalt with 2 ammonia and 4 chloride. Combined charge is -2. And the ammonia is 0 charge, so together 0. 4 chloride combined charge is -4. So you can easily find the charge on the cobalt. That should be +2. Okay, this is important. Okay, to study the magnetic properties, electron configurations of complex, we need to know how many d electrons in the ion, in the metal ion. The namings, we won't be spending time on that. We can see some examples. And each one, they have their own naming system. Some ancient metals, the name, the anion, we use their Latin name. Ferrin, the Fe, where the symbol come from. Ferrin, from ferrate. Lead is a plumbate because of plumbing, related to lead in the ancient times. Copper, Cu of copper come from the cuprium, and so forth. Transition compound naming, I'll just show you some examples. You can see the compound like this. Each one has its own names. The first compound, I just go through verbally. The name of the compound should be sodium hexafluoroaluminate. So that's the name for the first compound. And the second one, we need to decide what is charge on cobalt. The charge on cobalt, we're going to see the with one sulfate is two minus. There's 2 minus charge on the sulfate. So that means there's 2 complex ions. So that means each one complex ion, which have these all combined together, should give us -1, should give +1 charge. All of these come together, the charge should be +1, +1. And the En is neutral ligands. 2 chloride give you 2 negative charge. So finally, the compound with this should be the cobalt 3+ charge. And once you know the 3+ charge, you can name the compound. And that's how we name the coordination complex, but we won't spend time on that. Formulas. Yeah, these are some namings. If you're interested, you can do a practice, write down the formula. The coordination complex. Yes.
Is the naming going to be on the final exam?
No. Constitutional isomers. So the coordination complex, since the complex has multiple ligands, the geometrical relationship between those complexes and cause isomers, which means different compound, even though they have the same ligands. This is a good one. This is the nitrite ion form complex with the transition metal. In here is nitrogen form bond with the central metal. And the exact same nitrite, if oxygen form complex, it'll give you completely different compound. They will have different colors. So between these two, we call it constitutional isomers. We don't need to memorize each one. What kind of isomers. And these are the ligands that can form more than one donor atom, and you can form isomers among those. The stereoisomers are the geometrical or the optical. These two we call them cis and trans isomers. In the first example is where these are the ammonia molecules, and these are chloride ions. The 2 chloride on the same side of the platinum. So this we call the cis. Same as the organic chemistry. When they're same side, yes, cis. And in a different compound, the 2 chlorine on the opposite end of the platinum metal. So that's what we define as trans, and these two very different. Cis isomer for this, we call it cisplatin. It's actually an anti-tumor drug, just like many drugs named end with is IN. And the trans isomers have no effect on the tumor cell. There's some more examples of cis-trans, but I will not spend too much time. Left-hand, right-hand isomers. These are the inorganic chemistry. We see more. And the bonding in the complex ions, it is covalent bonding, share electrons. But this bond is fairly different. It's more reactive, easy to dissociate. So it has a special name, what we call a coordinate covalent compound. The bonding exactly use hybridization. This is kind of review what we learned before the hybridization. With our transition metal complex hybridization, it is also the mainly the d electrons hybridize. And once they form the hybrid orbitals, those hybrid orbitals, each one fit in the lone pair from the ligands. And this is the square planar complex ion. And you see the square planar, and you get a new, very interesting hybridization. Is DS2 hybridization. Never seen that before. It's only for transition metals. They explain the bonding and geometries. So these are the tetrahedral. This is also sp3, since as tetrahedral. The coordination complex of the transition metals often have colors, and the colors can be explained by the electrons transition among the d orbitals for those metals. And to explain the color in those transition metal complex, first we need to kind of quick review the color wheel. Color wheel is basically the across from the center, it is give you the complementary colors. Complementary colors. If a molecule or object absorb red color, for example, if example absorb red color, then this object would look like all the color combined together, which would be the green color. So if a substance absorbs one color, then the apparent color of this object should be the complementary colors. If something absorbs the blue light, the color of this object will be the orange or slightly brown. If a molecule absorbs the short wavelength violet light, then it looks like yellow color. Complementary colors. The crystal field theory, it is to try to explain how come the different transition metals, when we change the different ligands, you have a certain color change, and also the magnetic property change. The transition crystal field theory, it takes some time to get into that, but the theory explains as the ligand, it interacts with d orbital from the central metal. The interaction, which is a little bit repulsion, it causes 2 of the 5 d orbitals have higher energy than the rest of 3. So this is how the ligand interact with the d orbitals in the central metal, which is blue metal. And for the octahedral geometry, there's x, y, z, 3 axes for the d orbitals. And those d orbitals will have interaction with the ligands. For these two, dx, for these two orbitals, ligands is lined up right in confrontation with those ligands. So this will cause the energy level of these D2 orbitals higher. The interaction between ligand and d orbitals, 2 of them will go higher. And the other 3, dxy, dxz, dyz, these 3 d orbitals, the electron crowd is away from ligands, so the energy is actually lower. These we call them all lower energy orbitals. So in the diagram, we'll shows like this: 2 orbitals higher energy, 3 have lower energy. And when the electrons feed in those orbitals, they will start from the low energy level to the high energy level. So start from the three d orbitals without ligand interaction. These are low energy d orbitals. But with ligand interact, the repulsive force between ligands and d orbitals, it causes the d orbital energy split into the 2 higher level and 3 lower level. The energy difference between these two is the crystal field splitting energy. And this energy delta depends on ligands. Nitrogen, oxygen, sulfur ligands, they're all different, give you different the splitting energy when they interact with metal cations. So what we did to find out in the as chemists, it is some ligands consistently give a high frequency absorption, whereas the others consistently give you low frequency absorption. And they notice, chemists notice, cyanide, for example, always give you the very unique color, that is absorption of high energy, will give you yellow color. And also magnetic property tend to be very poorly paramagnetic. Whereas the fluoride ion will give you all water. These two will give you color more on the longer wavelengths absorption. And the magnetic property seems that there's more likely to be paramagnetic for the final example. The difference is the main focus of the crystal field theory. The crystal field theory basically explains, predict how the orbitals should split, the 2 low energy level with 1 high energy level, and also depends on the ligand. Some ligand tend to force electrons pair together, whereas the other ligand tend to allow more electrons freely unpaired and be more attracted by the magnets. So that's what we see. The water as a ligand, it causes the small separation between the d orbitals. It's a small gap. Delta is a small splitting energy. Small splitting energy, it allows electrons to take a different, the higher energy levels. The strong splitting by the cyanide, this kind of ligand, and ligand cyanide always tend to do like this, tend to force electron pair. Because the cyanide, when they interact with the d orbitals, it causes bigger gap between d orbitals, stronger interaction, bigger gap. So what is the difference between these two? When the energy level is small, electrons, they will first fill up the low energy d orbitals, the 3 low energy. And the number 4 electron will have an option. The number 4 electron either pair with the one of the d orbitals, which is already occupied, or you take a high energy level orbital. When the energy gap is very small, it's easier to overcome the barrier. Because if you electron pair, there will be repulsion between electron pairs. In this case, the repulsion between electrons is larger than the delta, because delta is so small. When the repulsion for the 2 electrons share 1 orbital is higher than the orbital splitting the gap, electrons tend to separate instead of share electrons. Yeah, they tend to not share or separate. if the energy gap between these two levels is very large, then the repulsion between the paired electrons will be less than delta. You can see the delta is very large. The repulsion less than the splitting energy, that will make the electrons tend to pair, because pair, you need to overcome a smaller energy cost instead of to take a different energy level. To take higher energy level, you also need more energy. So strong field ligands tend to lead to a larger splitting energy, bigger gap, and tend to share, electrons tend to share. So how do you know which ligand that can force us to share, or which ligand to allow us to spread out? Well, that is what we call a photochemical series. It gives us the capability among different ligands to interact with the metal cations. And the series will be given in the test. So basically, how we understand which one to form pair, which one to share, two electrons squeeze in. You can see in this case, two electrons share same orbitals. It's a little pushy. It's kind of there's a repulsion to overcome. The analogy I use for this, it'll be, okay, let's say we watch a movie. Okay, watch a movie, and there are 5 seats, 5 boxes. Each one maximum two people in one box. There are 5 boxes, and there are 3 boxes close to the screen, to the front. And when these two, the front row and back row very similar, the electron just move on to share to split into different, the layer, the back seat. Back seats, for those of you who watch a movie and even movie theater very large, back seats can be very difficult. But if back seat and front seat difference are very small, it's very easy to occupy the back seat. Okay, what if we have a situation like this? Another movie theater, also 2 rows of seats, total 5 boxes. The front box very close to the big screen, so it's very nice to watch movie. The second row for the boxes for the audience is way back. So the people sitting in the way back seat, look at the big screen, it looks very small. So in this case, because the gap between the two rows of audience, 2 seats, is so large, electrons would rather share the same box, even though there's repulsion. They tend to give fewer unpaired electrons. Whereas water as ligands is weak between these 2 differences, very small. The electrons tend to spread to fill up the gap. These tend to spread. And the other, when you have a ligand like cyanide, they tend to share or pair. Pair in the lower energy level. So that's the difference between the 2 different kinds of ligands. And the cyanide always tend to push electrons to pair. Water ligands, they tend to allow the electron to split, to share between the different orbitals. And between these 2, the first one has 4 unpaired electrons. This one's 4 unpaired electrons. Whereas the second case with cyanide, you have only 2 unpaired. The magnetic properties, it is fairly significant for each other. And the color can also be explained by the ligands. Those ligands cause a huge splitting, force electrons to pair. They tend to have shorter wavelength absorption, which means high energy absorption. And then the apparent color will be the complementary color. So in the octahedral metal complex, the ligand will interact with the 5d orbitals differently. And there'll be 2 orbitals have the repulsion, have the strong repulsion with d orbitals. The strong interaction, the strong repulsion between ligand and d orbitals cause these 2 d orbitals have higher energy. And so these are the high energy, as you can see from the energy diagram. The other 3 d orbitals occupy the lower energy because there's no obvious repulsion between the ligand and d orbitals for the remaining 3 d orbitals. And so after the splitting, then the d electrons from the metal cation will be able to occupy those d orbitals, but depends on the nature of the ligands. Okay. Some ligands have a stronger interaction or repulsion between the ligand and d orbitals, and some other has a weaker, relatively weak interactions. The one with a weak interaction between ligand and d orbitals, gap between these 2 small. So it's easier for the d electrons from the metal to occupy both, start from low energy 3 d orbitals, and any remaining will occupy the higher energy d orbitals without pairing. Because when the electron pair share orbitals, there will be repulsion. When the gap is small, the repulsion energy between electrons will be more than the gap between the 2 groups of d orbitals. So in this case, the electron would rather separate to avoid repulsion within the pair. That's with weak ligands. With the strong ligands, the stronger repulsion between the ligand and d orbitals, those 2 2 d orbitals, cause a bigger splitting, bigger gap, because those ligands energy becomes so much higher. You have a larger gap. Larger gap for electron to occupy, the repulsion between the paired electrons, the electrons that share in the same orbitals, repulsion compared with the gap is small. So instead of overcome the gap to occupy the high energy orbitals, the electron would pair first. And then any remaining electrons, any extras beyond 6 electrons, will start to occupy the high energy orbital. So they are very different in the magnetic properties. The color of the transition metals come from absorption of the d orbitals. And here's the explanation why there's color. The color or the wavelengths of light being absorbed depends on the ligands. Okay. The bigger gap, it'll require more energy for the d electron to transit from low energy d orbitals to high energy. Yeah, the color of transition metals complex, it comes from the d electron being excited, absorbed energy being excited to jump to reach the high level d orbital. And so the color, the weaker ligands cause small splitting. In that case, the d electron absorbs less energy, which means longer wavelengths, which means the complex will absorb longer wavelengths light to excite to jump to the high energy level. If the ligand is very strong, cause a big gap, big delta, then the d electron will have to absorb the shorter wavelengths light to transit to the higher level, d orbital. And so basically the ligand is strong or weak affect the color. Weak field absorbs longer wavelengths, which means that the apparent color based on the color wheel, it shows the higher frequency or shorter wavelengths light, such as purple, blue, and so forth. The weaker ligand, okay, the weaker ligand, the stronger ligands, the stronger ligands will cause the complex absorb shorter wavelengths. So the apparent color looks like a longer wavelength color. For example, the red, the green. So those ligands with the strong ligands tend to have those kind of color, very different in the color. And so these are some examples. A different oxidation state also affect the charge. Different ligands affect charge. This one's vanadium have two different oxidation states. This is the chromium with one different ligand. Instead of 6 ammonia, now we have 5 ammonia molecules with one chloride ligand. Even though the difference seems like fairly small, it's just one ligand difference. The color can be completely different. So what ligand cause the large gap, the large splitting energy between the two d orbitals? This is a sequence called a spectral chemical series. And this whole sequence will be given. Maybe you have a few more ligands. It shows you among different ligands, each ligand, how that will affect the gap between the two d orbital energy levels. The iodide is in the weakest. It causes the smallest gap between the d orbitals. And the cyanide or the carbonyl, this is what we call carbonyl ligands, it causes a very large gap between the d orbitals. And so when you have those effects, it affects first how many unpaired electrons in the transition metal complex, and also absorbs the light absorbs. Okay. The bigger gap complex ion absorbs shorter wavelengths. And when you absorb shorter wavelengths, the color appears to be the longer wavelength color, and vice versa. Water is considered as a weak electrolyte, weak field ligand. So that's the sequence. For our practice and for the future explanation, we'll just pick water and the more to the left, these are the weak field ligands. The more to the right are the strong field. So remember, they have big difference in calling the d orbital splitting. The magnetic properties depends on the number of unpaired electrons in the d orbital, the metal ion. Why it has to be d orbitals? Because the d orbital for the transition metal oftentimes the highest energy in the ion. And the other s and p orbitals with electrons all paired will not affect the magnetic properties. The magnetic properties cancel out. And with the unpaired electrons, it can be attracted by the magnets. And these we call them paramagnetic. This will be paramagnetic. The unpaired electrons, because we're dealing with the 5 d orbitals, the maximum unpaired electron will be only 5, and the lowest will be 0, which means they're either no electrons or all the electrons paired. And so those are the number of unpaired electrons. And so the two things consider how the electron population, the occupancy of the d orbitals, there are two things. One is the repulsive pairing energy. This is the energy when the electrons share same orbitals. And there's a repulsion between the two electrons. And the electron can also have an option to move up to occupy higher energy d orbitals. That they need to overcome the splitting energy delta. So two things combined together, depends on which one's bigger. If the pairing energy is larger than the delta, then the electron will not pair. If the delta is larger than the pair, with a weak field, with the strong field ligand, delta will be large. And when the delta is large, then the electron will pair instead of taking the different orbitals. Yeah, the relation between the pair and delta. And so here's the example for manganese 2+. Manganese 2+, we decide first electron configuration for the manganese 2+ charged ion. And for the manganese 2+, no ligands bound. The configuration should be 3d5, means the 5 unpaired electrons. But this is free, no ligand bound, no complex ions. With complex ions, with complex ligands, it'll cause an orbital split. So with the water molecules, it causes smaller split because water being the weak field ligand. And if you get a cyanide, this is typical strong field. You get a bigger gap. We have bigger gaps, small gaps. The difference is the pairing energy repulsion between electrons within sharing the same orbital. It is basically a constant. Pairing energy, E pairing is the same. But delta depends on the ligands. The weak field ligand, delta is small. So you get a pairings higher than delta, which means the electron to form pair need to overcome more repulsion than the electron occupy the higher energy orbital. In this case, because the delta is small, the electron would occupy different orbitals to reduce the pairing energy, minimize the energy. If the gaps are very large, then in addition to the 3 electrons occupies the 3 lowest orbitals, number 4 and all the other electrons will have to decide, should I overcome the repairing or overcome the barrier of going higher level. This jump to high level, the gap is too big. So for the electrons, maintain the pairing makes the system have a lower energy. So strong field push the electron to form pair first. Weak field allows the electron to separate first. So that's the difference between the different ligands. And if you compare the unpaired electrons, this complex have 5 unpaired d electrons. 5 unpaired d electrons. That's for the weak field. Since you have 5 unpaired electrons, this is called high spin, because there are more unpaired electrons, making them more attracted by the magnetic field. The strong field cyanide causes bigger splitting, and the electron would just prefer form pairs to avoid the penalty of overcome the high, the barrier of, between 2 layers. At the end results, you have only 1 unpaired electrons. That's a low spin, because only 1 unpaired electrons attract to the magnets fairly poor. This is 5 unpaired electrons. 5 unpaired electrons, and this have only 1 unpaired. And that shows the big difference between these two. So in our quiz, there will be this kind of questions asked about the, give you a complex ion, you decide what is configuration, and how many unpaired electrons in the complex, and will this compound be high spin or low spin? High spin attract to the magnets, and low spin not so much attract to the magnets. And so these are some typical examples about the for different configurations. The first one's 4d electrons. When the metal cation has 4d electrons, depends on ligands, the weak field, just weak field, be 3 electrons occupy the low energy and a 1 in the high energy. So in this case, you have 4 unpaired. 4 unpaired electrons is high spin. With a strong field ligand, the gap is very large, electron would pair instead of a separate. Here you can see there's only 2 unpaired electrons. That's when you have 4d electrons. The difference between strong field and weak field. 5d electrons. We've seen with manganese 2 plus. And here you have 5 unpaired. And here's only 1 unpaired. There's no need to memorize this, but you need to know how to find the configuration for the free cation, free metal cation, how many d electrons. And then you based on the strong split, which means the strong field, versus the low split, small gap between the 2d orbital energy level. You write a configuration. 6d electrons, you will have first 5 electrons occupy individual, separate orbitals. And with the number 6 electron, it has to form pair with the lowest energy d orbital, which is here. So here you have a 2 unpaired, 4 unpaired. And that's with the weak field. With the strong field, those electrons, because the large gap, they are the optimal choice for those electrons. It is just to overcome the barrier of repulsion, the pairing energy. So in the end, all paired, there'll be 0 unpaired. There's a 0 unpaired electrons. And the 0 unpaired electrons, magnetic property, we have a name for that. When all the electrons paired, we call it diamagnetic. Diamagnetic means repelled by the magnetic field, slightly repelled. And when you have a 7 valence, 7d electrons, first 5 is each one individual with a weak field, and then 2 more electrons, they have to pair. So in this case, you have 3 unpaired. 3 unpaired. With a strong field, 7 electrons. The first 6 form pairs. And in the end, there's only 1 unpaired. It's only 1 unpaired for the strong field. So in all these cases, it shows a big difference between the strong field and the weak field. If the d electron in the cations between 0 and 3, or between 8 and 10, in these cases, there'll be no difference between the strong field ligand or the weak field ligands. So for the when you have a below 4, number of d electrons below 4, it makes no difference. All the electrons will occupy the lowest, the lower level, 3 of the d orbitals. 3 d orbitals. And for the number of d electrons 9 or 8 or 10, there are too many d electrons, And then either case, the lowest energy level will be complete filled. And so the will be no difference between the strong field or weak field either, just because too many electrons. So that is the difference between the weak field and strong field in creating the splitting pattern and magnetic properties. Okay. So I just use one example here, the iron 2 from the complex in hemoglobin. And so the iron 2 in the protein hemoglobin molecule, it creates the functionality it is to bind with oxygen, transfer oxygen in the blood, as the word heme come from. So the iron form the complex. The iron 2 can form 2 octahedral complex. One is with 6 water molecules, and the other with 6 cyanide molecules. It should be 6 or minus. So what is the energy diagram for these 2 complexes? I identified the ions low spin or high spin, and which ones absorb longer wavelengths. So these are all under the crystal field theory. So to begin with, we need to find out the what is the electron configuration for iron 2 ion. So this one we start from the iron 2. Iron 2, the iron's is 26 electrons. The iron atom configuration, it'll be, I use noble gas, shorthand. The argon's 18 electrons, and iron atom has 26 electrons, so 8 more electrons. 8 more electrons beyond argon, so that'll be 4s2 and 3d6. So that's the configuration for iron atom. And what about iron ion, 2+ ion? When they form ions, you lose the s electron first. So the electron configuration for the iron 2+, it is argon 3d6, because you lose the electron, 4s electron first. So with the free iron ion, there are 6 d electrons. And the next, the orbital splitting. Now I can get to orbital splitting. The orbital splitting, first one with the water. The water is a weak field ligand. You can check the special chemical sequence series and find out water is a weak field. Water is weak. It's a weak field ligand. So the splitting pattern is a small gap between the 2 groups of d orbitals. Small gap. And with 6 d electrons, because the gap is small, the first one going here, the second one going here, number 3 going here. There are 6, so 3 more electrons. The number 4 electron would occupy the high energy d orbital, because the gap is small, so they will occupy high energy orbital. And finally, I have only 1 electron left, and that will occupy the low energy level, start from pairs. So that's with water as ligand, the configuration looks like this. Next one with the cyanide. Cyanide is strong field. Strong field ligand. With a strong field ligand, the gap between these 2 d orbitals is large. And when you have large d orbitals, the first 1 electron here, number 2, number 3. 3 more electrons, because the gaps are very large, the electron form pair first. And now we don't have any electron left. That's the strong field splitting pattern. And for the d orbitals, for the d electrons. So that is the question A. Question B, identify ion as low spin or high spin. The ions low spin hydrogen. Well, you look at the water as ligand. You can see there are 1, 2, 3, 4 unpaired electrons. That's a high spin. So basically 3 is a line. 3 is the division between high spin and low spin. Below 3 is a low spin. Higher than 3, high spin. And this is a 4 unpaired electrons that make it a high spin. Water as this. High spin ions. And then you look at the cyanide as a ligand. There are 0 unpaired electrons, 0 unpaired. Zero unpaired electrons. So this cyanide complex ion is low spin. It actually is 0 spin. And so that's how you know the metal complex ions. What is the magnetic property? Based on the number of unpaired electrons in the crystal field splitting prediction. And number C, question C, which complex has absorption at a longer wavelengths? Longer wavelengths, it is a lower frequency or lower energy absorption. So the lower energy absorption, it should be the one with smaller delta, which is the weak field, which means the water complex ion, the iron with water. It should give you the one with longer absorption at a longer wavelength. Okay, so that's basically how the crystal field theory applies to predicting the magnetic properties and the absorption frequency wavelengths for each complex ions.
Professor, I'm a little confused about part C. What feature about the two complex ions are you using to determine the absorption wavelength?
Use delta, the weak field. The delta is the energy to be absorbed by the d electron.
Okay, so if delta is small, then it's going to use longer wavelengths, but if delta is large, it's going to use shorter wavelengths.
Correct.
Okay, that makes sense.
Yeah. Yeah, the delta is basically the is energy for d electron transit from the low energy d orbital to high energy d orbital. There are some other absorptions, but those absorption energy involved are much higher, and it's in the UV or X-ray band. You won't be able to see that. With the visible light or infrared is d orbital transition. It affects the absorption, and that's actually we care about. And when the energy gap is very large, transition is very difficult. The intensity or the possibility is very, very small. It's not important. So the delta, the question C is based on the strong field or weak field. The weak field, it means smaller gap, and for the d electron will absorb less energy, which means lower frequency, longer wavelengths absorption. So that's how the crystal field theory applies to